Hello again. In this video we'll continue with our last example and we will see how to debug an AVR program using a simulator. In our example, it's a very simple program. We can test it in a board if we have one and check if it works, and we have seen it works correctly. But in a complex program, or if we don't have a board to test it, we still need to know if the code is correct or not. So to do so, we can use a simulator. In the instructions in the repository, you have also summarize the steps you can use to do that. Okay, so this is the debug using a simulator part. So the idea is as follows. We have our code here. Okay, and we have a terminal where we can execute our assembler. We will need another terminal, so we will open another terminal in the folder that we are using. Okay, I will put this terminal smaller because we don't need it to be as big, and we will make the other terminal bigger. So now the idea is that we have our program already compiled. This is the executable file we may upload, okay, to the chip. What we are going to do is that we are going to execute a simulator for the AVR chip, and the simulator will execute the program for us, so we don't need to have the real chip. And in the other terminal, we will execute a debugger. A debugger is a program that makes it possible to control the execution of another program. And the debugger will tell us how our program is running. So we can check the registers, we can check the variables if we are debugging a high-level language program. And we can see all the details, okay? So we have the instructions here. We only have to understand what we are doing. So first, we have had to assemble our program, including debugging symbols. This is the -G option here. Okay, so if we have assembled our program like that, this is fine. If not, we can execute it again. Great. So now we have our executable program ready. Okay, the main elf. So now we run the simulator. This is a simulator we have installed in the package sim AVR. So we just copied that command, sim AVR -G, which is the simulator will run the program, but will open a connection to connect with the debugger. Okay. The -M option is to add the chip number to simulate, because the simulator can simulate a whole range of different AVR chips. And now we say the main.lf, which is the file that contains the executable program for the AVR. So we execute it in the terminal, and now the simulator is running. The program is not running yet. It's waiting for a debugger to connect to port 1234. Okay, it uses a network connection, and it is very interesting because we can actually run the simulator in one computer and run the debugger in a different computer, but we won't do that this time. And now to debug the program, okay, we in the other terminal, in the big one, we execute the debugger. Is the AVR GDB, and we can put here in the command line the file that we want to debug. Okay, this is the version for the AVR architecture of the GDB debugger, the GNU debugger. The GNU debugger is probably one of the most used debuggers in the world. It can debug many different programs for many different architectures. It can debug programs written in almost any programming language that exists. And in this case, this is the version that has been cross-compiled to be executed in a regular computer, in a regular desktop computer, but that will debug a program for this computer where I'm executing it, but it will debug a program for a different architecture. Okay. So here we are going to use the debugger as is. This debugger doesn't have a front end or a graphical interface. In most development environments, they have a front end included in their graphical interface to interact with the debugger. In this example, we are going to use the debugger directly. It's a bit lower level. It requires knowing a few commands, okay? And it is not that you don't do normally if you want to do some simple debugging task, but it is something that is done when you want to make some more complex debugging operations. Okay, it's just an example. It's not that you want to use the debugger directly most of the time, but it's not that difficult, especially if you have a guide with the most common commands that you can use here. So we execute the debugger. Now the debugger is ready, but we have to tell the debugger where the program is running. Okay, so we need to configure it. So basically here you have the commands. This command is to be run inside the debugger. It tells the command to connect to a remote target, okay, because the debugger is the host, is the program that is doing the debugging, and the target is where the program is running. So we copy this command here, and the target is a remote target, which is in our computer, which is localhost, and at port 1234. This is the simulator, actually, the connection to the simulator we are using. So we execute that. The simulator noticed that the debugger has connected, and now the program is running. Okay? It's telling us that it have executed the first instructions in our program. Okay. Okay. From here we can use the debugger using commands, but the debugger also have a user interface which is activated with the TUE command. It's not a graphical user interface, but a terminal user interface, and it makes debugging a bit easier. Okay, because we can write commands here and we can see things here. So to move around in this terminal interface, we can use Ctrl X2 and Ctrl XO. So we are going to execute Ctrl X2, and we go through different configurations. Okay, here we see the source code, and we have the disassemble code. Ctrl X2 again, and now we can see the registers in the computer and the disassembled code. Okay, we press Ctrl X2 again, and this is the view we are going to use. That is the source code, and these are the registers. Okay, so this way we can check if it's working or not. And now everything is done by executing debugger commands here. If you see, we can make the focus on this region by pressing Ctrl XO once, Ctrl XO second time, and now we have the focus here. Okay, it's a bit clumsy, but it works. So now if we want to execute just a single instruction, we write the instruction step. Okay. If you see, the debugger is executing one assembly instruction. We don't see the source code yet because now the debugger is executing the code that initialized the execution. Okay, this is not the code in our main program. It is some code that the assembler inserts before our program, okay, to make some to prepare the system. So we just repeat the command step until we reach the starting point in our program. Okay, now we are in function main, and we can see the instruction that's going to be executed, and we can see how it happened, what it means with the registers. Okay. So that's it. Let's go for it. Now in the debugger, you can write the full command or just the starting of the command. For example, an S will do a single step. So we execute the LDS instruction. In R16, we are loading the value of the DRD. It happened to be 0, so nothing have changed. Now we are going to use an AND operation on R16, so we execute another step. We can put an S, or we can press enter right away. If you just press enter, it will execute the same command as before. So the AND doesn't change the value in the register, so we don't really see anything changing, and here as well, okay? But it's what it's supposed to happen. R16 is 0 and it's configuring D. Now we loaded, now we want to activate the pull up. So we load R16 with this value, and now we see that it have changed. You see here, okay? This is 100. This is 80 in hexadecimal and 128 in decimal. Okay, so it worked as expected. We store it in our port D register. Port D is actually a memory address where the register is mapped. Memory is not shown here directly. We can print memory. You have a short guide how to print memory, but you can print anything if you write the name. For example, if we write here print dd or port D, okay, we see the value here. So we can check that the memory address port D has received the value we have just stored there, okay? Actually, it is easier to use another command, which is, we can repeat commands if we want, okay? Instead of print, we are going to use the command display, okay? Because display is like print, but display will remember what we want to print. So anytime the debugger executes some operation, it will print the value of that port again. And we are going to do the same with pin D, which is the input. Okay, and we are going to do the same with port B, which is the output port. Okay, so this time we'll get everything we are interested in printed at every step. So just execute things step by step. We execute another step. Then now this is the DRB. This is going to be ORed with this number. Okay, the number loads here. And we can continue like that. Okay. We store in DDRB. Okay, so we step again, and that's it. We can check that if we have actually DDRB we don't have here, so we can print it DDRB, and we can check that we have stored that value. Okay, this is 32 in decimal. Okay, great. Now we can continue step by step. Normally, if we are going to do it once, step by step. So the important thing is that pin D now is we have activated the pull up, okay, in port D. So the input is set to high value. Okay, so the output in port B will have to change to the high value. So we load port B, we step, we load pin D, we do the AND operation. You see here 80, we do the AND operation. It happened that it's not 0. Okay, so we are activating now the port B output. Okay, you use R17. It has changed the value, so it's highlighted here, and then we jump continue and we set the port B. So here port B has not yet been set, and it's set after we execute that, and then we go back and repeat again. Okay, So we repeat again, and because the input is 1, so the port B will be 1. What if we want to change the value? This is the pin D. Now we want to set the pin D to 0. So we can set it with set, a command, and we put a register or a memory address, and it will change the contents of that address. So we'll set pin D equal to 0. It means all the bits will be equal to 0, including bit 7. Okay, now it is we can print the value if we want to check. Now it's 0, so we will just continue stepping through my program. So we load port B, we load pin D. If you see now, what we load is a 0. We branch shift 0, and this time we jump to the part of the program that activates when it's 0, and the result will be that the new value to be stored in port B will be 0. So after we execute that, port B is now set to 0. So we have checked that depending on what we put in pin D, we get the same result in port B. Okay, now we have executed the program step by step. Normally, you don't want to execute all the instructions in your program manually. You can make it happen a bit faster. Okay, so to do that, you can set breakpoints. So, for example, we can change the window here. Control XO. We are in the source code window now. Okay, so we can move with the cursor keys up and down, and we decide, okay, we want to repeat my program. We are going to load pin D. I'm doing the end. So we want to stop my program exactly here at line 21. Okay, before we take the decision if the result is 0 or not. So we can set a breakpoint. I think it's the breakpoint command, and we set it at line 21. I don't remember how it's done. Yes, it's not breakpoint, it's simply break at line 21. Okay, you can use a label here. We can say break at loop or break at this label, but I think we can break, okay, at line 21. Okay, so now what we can do is just tell the debugger to continue the execution, okay, and it will stop here at this breakpoint. And here we can check. We have pin D 0, port B 0. Okay, so we are going to change. If we continue again, it executes all the loop and stops here again. So we can change the pin here. We will move to the bottom part. We can repeat. We will set pin D equal to 0. Now we will set pin D equal to 128. Okay, to activate the 7th pin. I think we can use binary format as well. And now we can continue the execution, and hopefully everything has gone around. Port is 128, and we have not taken the decision yet. Okay, I think we have to continue again. Okay, now so in the next pass of the loop, now the output has been activated. Okay, so this is basically how we debug programs with a debugger, and we can do it even if we only have a terminal and the basic tools. Okay, we will see in future videos how to do it from inside an integrated environment, but this is how it works just by looking at the tools that are really run. Only that our integrated environment, they just run the debugger in the background and communicate with the debugger through the commands, sending commands, and then they will render the result in a more intuitive interface probably, okay? But you can use the debugger directly if you really need to, okay? So to stop the execution, we can press Ctrl+C in the terminal or the interrupt command in the debugger. And just to get out of here, we press Ctrl+C, Ctrl+C again. Probably it's quit now. Yes, we want to disconnect, and here it is. And here in the simulator terminal, we just press Ctrl+C, okay, and we cancel the program, and that's it. Okay, so this is the basics of debugging. Thank you.